Let's see how to plot data for a first-order reaction. So the conversion of cyclopropane into propene is a first-order reaction. And in part A, they want us to use the experimental data to show that it's first order. So we look at the data over here, and we can see as time increases, right, the concentration of cyclopropane decreases, which makes sense because cyclopropane is turning into propene. If we want to prove this is first order, we need to use the integrated rate law from the previous video. So in the previous video, we showed that the natural log of the concentration of A is equal to negative kT plus the natural log of the initial concentration of A. And for this reaction, A is cyclopropane. So we could write this as the natural log of the concentration of cyclopropane, C3H6, is equal to negative kT plus the natural log of the initial concentration of cyclopropane, which we also talked about in the previous video, follows the form y is equal to mx plus b. So if we put the natural log of the concentration of cyclopropane on the y-axis and we put time on the x-axis, if we do that and if we get a straight line or close to a straight line, then we know that the reaction is first order. And the slope of that line, right, m, should be equal to negative k, where k is your rate constant, and the y-intercept, right, should be equal to the natural log of the initial concentration of cyclopropane. So if we're going to graph that, right, we need to figure out the natural log of the concentration of cyclopropane, right? So right now we have only the concentration of cyclopropane. We need to take the natural log of all these numbers and before we graph something, right? So we need to take the natural log of 0.099. So we get out the calculator here. So natural log of 0.099 gives us negative 2.31. So we put negative 2.31 here. Next, the natural log of 0.079, so the natural log of 0.079, and we get negative 2.54, so negative 2.54. Next, natural log of 0.065, so the natural log of 0.065 gives us negative 2.73. So this is negative 2.73. And then one more. So the natural log of 0.054, natural log of 0.054 is equal to negative 2.92. So we have negative 2.92. And so now we're going to do the natural log of the concentration of cyclopropane on the y-axis, right? And we're going to do time on the x-axis. So let's go down here and look. I already have the axes labeled, right? So on the x-axis, right down here we have time, and on the y-axis we have the natural log of the concentration of cyclopropane. So let's figure out some points. Let's figure out some points here on our graph. So when time is equal to 0, right, y is equal to negative 2.31. So when time is equal to 0, we have negative 2.31. This is negative 2, so this is negative 2.1, negative 2.2. And so this would be negative 2.3. So negative 2.31 would be pretty close to there. And obviously, it's very hard to graph something perfectly given what we're trying to do here on this video. So I'll just say that's approximately negative 2.31. Next point is that when time is equal to 300 seconds, we have y is equal to negative 2.54. So 300 seconds would be here. 2.54, that's pretty close to here. All right, so we'll say that's approximately that point. Next, time is equal to 600 seconds, negative 2.73. So we have 600 seconds. 2.73, this would be negative 2.6, negative 2.7, so negative 2.73, close to there. All right, certainly not perfect, but close enough. All right, and then finally, time is equal to 900 seconds, negative 2.92. So 900 seconds, negative 2.92. Would be pretty close to there. All right, so let's see if we can draw a straight line through those points, or pretty close to being through those points here. So we're putting a line of best fit, right? Let's see what we can do. Well, that looks pretty good, actually, all right? So we put our line, and our line is pretty close to passing through our points. So the points fall on our straight line. So we can say that the reaction is first order. All right, so this reaction is first order. We plotted everything, and we got y is equal to mx plus b. So we're done with part A. Because we got a straight line here, right, we can say that this is a first order reaction. All right, for part B, our job is to calculate the value of the rate constant. And the rate constant, remember, let's go back up here, the rate constant is k. And we know the slope is m, right? So the slope of that line is m, and the slope is equal to negative k. So let's go back down to here. So the slope of this line, is equal to negative k. So we can find the slope a few different ways. One way would be to do delta y over delta x, right? So your slope is equal to change in y over change in x. So if you picked a point here and you picked a point here, right, you could figure out your slope that way, right? So I'm just showing you what the slope would be. This would be delta y right here, and then this would be delta x. Your units would be 1 over seconds, right? So your units for k are going to be 1 over second. And we could have figured the units out a different way by using the rate law. Right, so this is for writing the rate law for our reaction. The rate of our reaction is equal to the rate constant K times the concentration of cyclopropane to the first power, because this is a first order reaction. Right, so the rate of a reaction would be in molar per second, and so this would be times K, and then we have the concentration would be molar, and this is to the first power. So obviously, right, molars would cancel and you'd get k is equal to 1 over seconds. So however you want to think about it, the units for k will be 1 over seconds. All right, so we could figure out some points and calculate k, but we wouldn't get super accurate value for k using this graph, which we just plotted by hand. So let's go ahead and get out the calculator and let's find what k is using the calculator. Right, so we can plug in our points. This isn't the calculator I'm used to using, so it's actually a little bit more difficult on this calculator than the one I usually use. But we can do it. We can go to Stat, and then go to F2 for Edit, and then hit Enter twice, and then we can start putting in our data points. Right, so when x is equal to 0, right, y is equal to negative 2.31. Right. Next, when time is equal to 300 seconds, when x is equal to 300, y is equal to negative 2.54. When time is equal to 600, right, y is equal to negative 2.73. And then finally, one more point, when time is equal to 900, y is equal to negative 2.92. So we have all of our data in there now. We can exit, we can go back into Stat, and then hit F1 for Calc. All right, so that's what we want. Hit Enter twice, and then we want a linear regression. So that's right here. We want a linear regression, so we hit F2. And B, right, B is M. B is the slope. So the slope of that line is negative 6.7 times 10 to the negative 4. All right, so let's go ahead and put that in here. The slope is negative 6.7 times 10 to the negative 4, and that's equal to negative k. So obviously k, or the rate constant, k is equal to 6.7 times 10 to the negative 4, and this would be 1 over seconds. Right, so we've now figured out the rate constant. Right, so we've proved that this is a first order reaction, right, by graphing our data, and then we found the value of the rate constant by finding the slope of our best fit line.